I deeply thank the organizer to invite me for this talk, and I really appreciate so everything is perfect. So I really appreciate. So this the talk is about the backward stochastic differential equation we call BSDE, nonlinear expectation. And recently we gave a bridge between the two, which is nonlinear PDE, which is PDE, but which is not Euro PDE, which is path-dependent PDE. So such kind of PDE, in fact, ignored for a long time for probabilistic point of view, because it's usually called random variable. It's usually called random variable, and then it's in fact very well post PDE, and it's also give so I begin with so this also give us a new point of view for also for PDE. It's involved almost 2/3 type of PDE. Okay, the PDE, linear or nonlinear, which directly link to the stochastic problem. And what I want to talk about first is the necessity of introducing a new kind of mathematical tool. Sorry, it's to solve a serious problem of probability and distribution uncertainty called Knightian uncertainty. I will mention later. In probability theory, in stochastic analysis, and in statistics. So this is we still face many challenger problems. The second is to introduce the nonlinear expectation theory. In fact, I already gave a talk in my ICM plenary lecture, and it's to introduce the theory. And since then, this is 2010, and since then there are big progress, especially many strong and young people come, join, and get a very beautiful result. And the bridge. The bridge is between partial differential equation, PDE, and path-dependent, a new path-dependent PDE, what I posed as a problem. The name was given in ICM 2010, like a path-dependent PDE. Can you formulate it? Can you solve it? And now there are many progress in this. We can also have a new platform. So the second is the link of a nonlinear PDE to probability, which include the probability theory, stochastic analysis, and the statistics, very important, and the optimization, and also for numerical computer, how to do it. And also it links to stochastic differential equation, so SD stochastic differential equation, and backward stochastic differential equation, which is also one of my lecture contents in ICM 2010. Of course, I realize that the lecture is addressed to big audience, so I want to make not really speaking in the language of probability. language, stochastic language, to try to make things more easier, have more easier access to this very attractive field. And I also, in fact, the theory of nonlinear expectation in itself is very basic and fundamental. In fact, I have lecture notes. In this lecture notes, I begin just from not. I don't assume that you have probability specialist of probability training. And it's just a very basic functional analysis and theory. Now, we all know that the probability theory is introduced by Prof. In his book, very famous book, Condition for Probability. Condition theory of probability, and then after then, of course, the triple omega fp, which is you have a measurable space, and here you have a measure probability, becomes the standard in every probability papers and books. So this also solved here was 6 problem to give axiomatic foundation of probability, and since then probability have a big progress, especially Shige in his famous work in 1942 is a great push to this theory. I benefit a lot from Shige theory. But on the other hand, even in 1921, Knight, which is who is the founder of economic school of Chicago, have a very famous book in economics called Risk, Uncertainty, and Profit. In this book, Knight don't believe that probability and distribution can be applied in economics, in business, and in finance. He don't believe that the people can really have a probability measure, and also for distribution. So what he called risk is probability unknown or distribution unknown. But the so-called Knightian uncertainty he introduced is for the case where probability or distribution are unknown. So this is called uncertain probability and distribution, and this is the objective that we want to work to really get some theory which is compatible with the probability theory, which is get a lot of so huge success. So this kind of Knightian uncertainty is very well known in economics. For example, they have there is Knight, there is the same year Keynes he also did. And the famous Alice paradox tells us that the well-known von Neumann Morgenstern expected utility expected utility theory use expectation is cannot be worked. And there are many other people. They are all Nobel Prize of Economics give and Thiel, the Hansen and Sargent is robust control method. So it's this, and also in finance, statistical method cannot really apply. It is well known that, for example, in intellectual theory, the most important tool is calligraphy. Is not statistical because they just use implied volatility, and also the many stochastic model of finance random variable and the stochastic process are assumed to be like the things that they can know the distribution, they can know the stochastic process. For example, intellectuals, they use the so-called geometric brand motion, which means that we can know the brand motion, its volatility, expected return. All such kind of thing is in fact is not true. People always use it and they know it's not true. This is a big problem. With this big problem, I think the last economic process is related to this. Related to this because they don't know how to do, and they try by this, and this becomes bubble. Okay, it becomes bubble because it's not true. It's not true. They just apply this formula for their purpose. So there is a big problem in this case. And the problem is related also for statistics to find the distribution f theta for parameter theta of a risk or random variable x among all parameters distribution. And this is not, at the other side, I believe that we can, in many cases, you can just not find it. So this is also a big challenge to statisticians. So all this deeply involved the point of view. Can we really find the distribution of from the given data, even big data? Can we really find it? So this is directly contrary to nice strong arguments against the such kind of against the known probability. So we in our approach we accept model uncertainty, probability and distribution model uncertainty. So we don't try to find this true f theta of distribution, but we still can establish a new type of model, which is also a distribution model, but under the language of nonlinear expectation. We still can find. For example, we can use the most typical model. Instead of normal distribution, we have such kind of new distribution, which is still parameter, which still can be estimated. But this is fundamentally assuming that the model has uncertainty. So it's not just one distribution, it's a package of distribution. But you can calculate it numerically. This is the main difference in this new theory, of course, which I want to. And also, we can also define the so-called worst case distribution, which has two parameters. In fact, we have many such kind of distribution, which is parameterized, but which based on the uncertainty of distribution. But they also give a new task to statisticians to estimate such kind of parameter like or still others like Cauchy distribution, like Poisson distribution, which still have such kind of. So we can. And for example, for calculating the normal T-normal distribution, we can define this UTX like this. If this is a normal distribution, classical normal distribution, then we know that this UTX is a solution of a Hit equation. Because this just said that this is you have the kernel of the kernel of normal distribution of a Hit equation. The Hit kernel is normally distributed. It's well known. But here from here we define this, and we can calculate this function, which is still PDE, but which is the so-called GPDE with sigma, two parameter sigma, upper sigma and the lower sigma, with the upper sigma, which is a function of sublinear function. This is the sublinear function with two parameters. When upper sigma equal to lower sigma, G equal to G is linear, then it's normal distribution. In fact, our equation, G equation, is written like this. It's a PDE. Okay, this is the fully nonlinear PDE, but it's a PDE in which if G is linear, it becomes Hit equation. So it's very simple to be calculated. And the new normal distribution and the maximal distribution can be easy to calculate. Recently, they developed many numerical methods, numerical algorithm for this. But another question is why you use this sigma square, G normal distribution and maximal distribution. This just because there is law of large number and the law of central limit. We still have another law, such kind of law telling us that under latent uncertainty, you still can have things to distribute. Okay, the theory comes even earlier than common law. The theorem is simple because in that year, in 1921, there is Daniel's expectation or Daniel's integral. Daniel gives this spectrum, gives such a so-called linear expectation space or Daniel integral space, in which we have a random variable which is a real function defined on omega. Omega is a domain. So they have this kind of function, which is in a linear space, of real functions, just satisfies this, the so-called lattice vector space. So x in H, then the absolute value of x is in H. It's very simple. And he assumed so from here we can define E, linear expectation, which in fact integration of a function. How we define? We just assume that it's this E. First is monotone, so second is keeping constant, third is linear. So that's all. Then, of course, we assume that when it's downward continuous. And it's well known from this we have a Daniel-Stone theorem telling us that there exists a unique probability measure P defined on this domain with the sigma algebra of H, such that Ex, the defined this E, is really expectation or integration of this P. Okay. This is his theorem. This theorem, of course, still based on the problem that you can know a probability measure. If you want to work for the situation where you cannot find the probability measure, then you can just work in the case where this E is sublinear or nonlinear. Sublinear is a very technical situation. We began with sublinear, but we can go still before to nonlinear situation. And in this case, A is A, B is still B, but C is sub-additive instead of equality. You have inequality, and then it's CD called is sublinearity. And if we assume that E is downward continuous, then they still have the so-called we call the robust Daniel-Stone theorem, which is telling us that there exists a family of probability measures defined on the same measurable space, such that E hat x is the supremum of this expectation or integration. So this is our basic. We base on this and we use this so this is the uncertainty subset we have. But this means that in fact this is if and only. Of course, if you take sup, you have this, okay, which satisfies A, B, C, D. And so we don't make like if only. So we just can work in sublinear data space. We have, and also from here we can also get the uncertainty of the distribution. Okay? The uncertainty distribution is all still given here. So with this we can really have something. And then we can have we can define what is the distribution uncertainty if X is identically distributed with Y, means that for H5 we can have this. This is classically correct, but here the meaning becomes that the uncertainty distribution of the subset of X is the same like uncertainty distribution subset of Y. And also we can also introduce the independence under such kind of negative uncertainty. Okay, the independence also. And with this, we have central limit. The central limit theorem telling us that if you have a random variable, in fact, there is functions defined here and defined on this space. If this random variable are NID under negative uncertainty, then we have the same convergence to X, which is which gives us the normal distribution, under this case. But I should emphasize that even in this case, it's not so simple that the uncertainty distribution is just between the normal distributions between sigma and sigma or lower sigma and over sigma. It's not such simple. In general, you need to calculate the PD or the TPD I just mentioned. So it's directly linked to PD. Another normal, the law of large number is the same thing. It's linked to PD. Everything is linked to PDE now. And the law of large number also tells if Yi is ID, and then for each phi, we have this converges to phi V. So this which converges to this distribution. This distribution is the uncertainty of the delta distribution. Okay, Dirac distribution, uncertainty of Dirac distribution. So it's and this distribution also linked to a very interesting PD. And you put them together, it's still have another PDE, combination of PDE, which is second order. So it's this kind of thing. And another thing is that this theorem is more difficult than the central limit theorem, and the proof of central limit, because it's degenerate. It's connected to a degenerate PD. And the proof is not at all trivial. It's based on a very deep result of Cafarelli and Lihe-Wang and Krylov for the triviality of solution of PD, GP equation. And also for stochastic process, we can also give the distribution uncertainty, probability uncertainty, but still we can have parameters, very simple parameters, stochastic process like a Brownian motion, like a typical Brownian motion. The Brownian motion is also defined very classically, but on this space. So we have B is called G Brownian motion if is the increment is independent from the things come before, and also the increment is the same distribution as before. Okay, this is very it's very likely, but also we also assume this. This if you have linear one, this of course you can prove this just Brownian motion. But here we can have the most technical situation of parameters Brownian motion, because we have two parameters here. We have lower sigma, we have upper sigma. So this can be can be still estimated. So we have such kind of problem for estimation. And the constructor of G brand motion linked to what I call path-dependent PD, what I mentioned in 2000 as a question in 2010. The construction is that we need to construct our omega here is a continuous path. Okay, here is a continuous path. And the brand motion is just the path. Each continuous path is the brand motion path, running motion path. And then they need to define H, the random variable or functions defined on H. We define the axis just like in notes. It's defined like this. X, we just need to think about the very regular function in which you have the path. So of course the path changes and then the value changes. Okay, the value changes. It's very like C infinity 0 for have you mentioned this? It's very clear, very simple. The idea is very simple. And then we have this, we can, for each x defined like this, we can set a sublinear expectation defined by this. And where this is the G expectation, this is the G normal distribution, this is G normal distribution. But we assume that this psi 1 plus 1, I plus 1 is independent of psi 1 psi I. And each psi is normally distributed, is in Knightian sense. And we define like this. Remember that in fact for calculating this G normal distribution, we need to calculate PD, which is G heat equation, which is just a little change of heat equation. If you then we can and the conditional expectation, which is a very hard topic before, is here is even easy, just because here we just need, for example, for calculating conditional expectation with T, we just need to put a constant here and calculate the other, and then after put x equal BT1. This is already finished. So in some sense, conditional expectation is getting before expectation. This is the one, and another thing is so all this procedure is very like Wiener's original procedure, but the only thing is that we calculated all this kind of thing backward. Okay, backward. So if you want to calculate this one, in fact you first calculate this one, and then the second one is the last one. So backward. This is a very important thing. And another thing I will mention later. This in fact here already involved the path-dependent PDE and G expectation, which is like here, omega equals C0 is the same. The continuous path begin starting from 0, and also omega. We also have this omega t, which is the continuous path between 0 and t. And we define still the random, the continuous path, and then we consider this kind of space space, which is our basic space, which is still defined like this. And then, in fact, what we did in the last slide is to calculate this PDE. To calculate this PDE by reading this PDE. By reading this PDE, like you have T here, you have omega T here. By reading this one. In fact, we solved this one, but it's in this past case, it's better to read the solution of this one to be this one. Okay, this is another point of view. This point of view is important for the case where if we work, this is the so-called state dependence. State dependence means that this omega t is the path at point t, the path value at point t, and then in general we already defined this path dependent PDE. Path dependent PDE, in fact, is like this. This is typical path dependent PDE. First, our state process is t and omega t, which is in the place of x, and then the path before t is assumed to be parameters. And what we did is really solve this PDE, okay? To solve the PDE of a classical PDE of this one for each time interval. And we did it backward. And then from here, in each interval, we solve this PDE, which give us UK, and then the UK began from UN, and the UN is the last term, the last term. Okay, UN is last term is this is capital T, and then we solve it one after another to this P. So this from the problem we solve is classical PDE, but with the connected condition. The connected condition is after you, because we work it backwardly, then you can get one after another. And from this, another very important thing is how to determine the weight. The weight of this PDE gave us a Sobolev word, norm, give us a Sobolev norm. This norm is in fact given by itself. It's given by itself. This idea is already in linear case is already used in Edo's framework. But here, because the expectation is sublinear, is not really very clear. But we need to specify that for each x, we give this norm. This is our LP norm. Okay, this is our LP norm for path function of path. Say it's function of path, we get this, and then we get such kind of LP norm. And also we can we know that in fact the conditional expectation we are given is in fact ut, which depends on omega, where omega is only before t. The path of omega is only before t, which is in fact, if we define this, in fact, which is path, the solution of path-dependent PDE. Here is very important, and its path-dependent PDE is the so-called margin. Okay. So it's established the relation between marginal and the path-dependent PDE. In fact, what we call marginal is also can be regarded as a solution of path-dependent PDE. So, but here the norm will be because here we still in smooth case we need to go further to define this path-dependent PDE, which is already defined in last slides. But here we can for continuous for smooth case. But now we with terminal variable, and we now can go further to. In fact, in this case, we can see how we can define the Sobolev space. The Sobolev space, recall that the classical Sobolev space is given omega, which are subset of Rn, and then U is in this C infinite compact support. And for example, this norm can be defined. It's very easy to define this norm, and then extend, take a completion of this. We do the same thing, but we use nonlinear expectation. We just use nonlinear expectation to define, to follow this line, to define. Because in our case, our omega is a continuous path. It's a continuous path. And then we can define now the path. I think I go directly for defining. First, we can define the path, and then we can also define the functions, the processes, which is path process, define on path process. And then we need to have such kind of cylinder functions, which is almost the same, but they depend path like this. Like a discrete T omega T. This is a very important path because we will take PDE here, but the other side are just the UK is classical smooth function, but defined like this, and with connected condition, and then what we define for T, for example, the derivative with respect to T is just you have this concrete function and you derive by T. This is very simple. For nth order, it's the same thing, but for x, for defining the x, it's just for the I side. We fix this x1, xk. Only take derivative of x. This part is very important, and which is different from, for example, Marialanke. Okay. We just take this part for derivative, which is the first omega, and then to the x equal x omega t, x1 is omega t1, and etc. And then the second and third order are all defined like this, and also we can define the Laplacian like follows, and this is the Magellan calculus. The Magellan calculus for this is just correspond to this situation. The situation is. And the other, this is related to the other so-called reduced derivative, also in the case where we don't need to assume that our space is jump space. But essentially, the definition is the same, but defined on the concrete cylinder space. And after this, we can have we can define the value by always taking the sublinear expectation and to have this value, and also to define the soft-left norm by this manner. With this, we can define a space of U, which is on the completion of this space, and under this norm. And we can also define this U2 T is also U12 T under U2T and also under this W2T. Now, and then we just take a completion. After the completion, it's easy to prove that all this operator, differential operator, can be continuously extended to the large, to the extended space. And we have the following proposition. We just assume that the process U is defined here, and then the following two conditions are equivalent. First one is U is already in this W2G space. The second one is that this U can be written as can be written like this. Okay, like the Edo's process. It can be written like Edo's process, and the relation between the two is that, moreover, in fact, this is nothing but the dt part. This is nothing, this v is nothing but the dx part. This is nothing but the d square x part. So, in fact, you read even Edo's formula for L2 process in a different way, and which give us the new point of view for example for the PDE, for the relation between BSDE and PDE in such way that, for example, a very interesting example is that if we define UT omega to be the theoretical variation process, then we can prove that it's just because of the formula. We can prove that dTu equal to 0, dxu equal to 0 uniformly, and d square u is not, is equal to 1. There are many such kind of very interesting situations we could do, and we could also did for BSD. Okay, the BSD solved by this part, this way. And I have no time but all kinds of, even in classical situation where P is Wiener measure, for the case where T is linear, we still have many interesting point of view, and which is linked to our BSD. classical BSD. Okay, the classical BSD is given this, and it is the fundamental work theory is given in this, and this always can read always PDE. So you can use PDE language to do for Markovian situation and non-Markovian situation. So there also give a deep relation between this. This question was proposed in 2010, and then now we can solve. We can solve this, and we can. There are still another very interesting formulation, and we still can many things have done, but another we have still many challenging situations. So I think there are two things to what I want to do, but I have no time to finish. So thanks.
Thank you very much for your nice talk. Is there any question or comment?
Maybe you here.
I don't know if so in the properties of the process U, when you have a representation formula and then yes.
Yeah.
So your conditions, so belonging to infinity,
Yeah.
that means with respect to G as a function.
To T and X.
So that means that it doesn't apply to the Brownian motion itself, so the classical Brownian motion.
No, it is because it's a function of the motion. So the Brownian is function of path. The path is Brownian motion. But here, because I just use the definition of dx, it's just I read here. You have u t omega t and omega t1 omega tk. Here, this is the Brownian path. Of course, it's very, very irregular. Okay, but my definition is that ut as concrete function of x and the concrete parameter of x1, xk is regular. This is regular. Okay. Thank you. This is for indicating.
I have another question, if I may. So you also presented some result of the central limit theorem of all Latin numbers. And then there was a parameter alpha, the interrelative condition. So alpha is what? Is
Alpha this alpha is like one is alpha is in zero, but it's not it's between 0 and 1. Is for any given alpha is okay. Because what I define is like this x 1 is 2 plus. So there exists alpha bigger than 0, such that this x1 is smaller than this. This may be still to be done from the work in to summarize alpha because classical solution 2 is nothing, but till now it's still a very interesting program. Thank you.
Any other question or comment? Then let's take